Now let's focus our attention towards our flagship CAM module, which is going to be the Visual Mill product. So I'm going to turn the attention over to the Mill module in here. So selecting VisualCAM and Mill automatically displays your Mill interface. The Mill interface has two main browser windows. We have the machining browser, which has two main tabs, Program and Simulate tab. And then we got the machining objects browser, which allows you to manage tools, your machining regions, hole feature detection, and also knowledge bases. So we'll touch upon the features in the machining objects browser as we go along during this webinar today. Now first, we want to go ahead and take a look at the different types of methods that are offered in our Visual Mill module. So we have 2-axis methods, which offers a wide range of methods starting with facing, pocketing, high-speed pocketing, profiling, V-carve roughing, engraving, chamfering, hole pocketing, and grid filling. Visual Mill also offers a wide range of 3-axis toolpath methods, roughing, re-roughing, finishing, remachining, pencil tracing, advanced finishing, curve-based machining methods. Visual Mill also offers 4-axis, both indexed and continuous methods, and also offers 5-axis, indexed and continuous methods. The hole machining methods are also offered, starting with drilling, tapping, bore, and reverse bore, and also in 4-axis. And there are several miscellaneous methods, and we'll take a look at them as we go through this webinar. I would now like to go over an example of programming a part using 2-axis. So I'm going to go ahead and load this part into VisualCAD. So we got this part loaded in here, and without any further delays, I'm going to show you how best we can program this part. So I have this part loaded in here, as you can see, and the first step in programming this part is making sure that the part that you've imported is in the correct model units, and then you want to establish the orientation of the part. So once you've established that, you can go ahead and define your machining process. You can define the machine tool, you can set the number of axes to be 2, 3, 4, or 5 axes. So for 2 and 3 axes, we'll pick 3 axes in here, and then we'll pick OK. In the next step, we would like to go ahead and select the post processor to be used to output the G-code. As I pointed out earlier, our CAM module offers a variety of different posts. We have posts for over 200 plus different machine controllers, so which covers a wide range of CNC machines tools that are out there. Now for this particular part, I'm going to use Haas as the current post processor, and then specify the posted output file. This could be set to NC, or you could use whatever is the preferred extension that your controller expects. If the extension is not available in the list, you can pick Add New to add your extension. In the next step, I would like to go ahead and build my stock blank, so I can click on the stock menu, and we have different types of stock types that we can define. So I'm going to go with the box stock in here, and the system automatically computes the minimum stock extents based on the part that you've imported. And I'm going to go ahead and specify my stock thickness to be 2.5 inches, and let's go ahead and pick OK. And you'll now notice that the stock is now defined and appears under the machining job. You can click on Show Stock Visibility, and the stock appears right on top of the part in your viewport. You can turn off the display of the grid if you prefer, and there it is. There's your part and the stock. In the next step, I would like to align the stock to the part, so I'm going to pick Align and choose Align Stock, and I'm going to set the alignment of the stock to the bottom in the Z, so the stock is flush to the, so I could face the material off from the top. And then I'm going to have it aligned to the center in X and Y. So once you have the stock and the part aligned, in the next step we could establish the origin of your workpiece. So you can use Set World CS, and you can choose where you would like to establish the origin. So I typically like to prefer setting it to the top, the highest face, in the Z, which is the highest Z, and then pick the southwest corner, which is over here on the left corner. When you pick OK, your workpiece origin or your work 0 is set to the top face and the southwest corner. So when you switch over to the Simulate tab, you'll notice that your program 0 or the work 0 is set to the top face of the stock and the southwest corner. In the next step, you're now ready to program some toolpaths in here. So I'm going to go to selecting the machining methods. Now before I pick the machining methods, I can also select the material type I would like to use for programming this part, and I can choose them from the available materials in the list. And for this particular part, I'm going to pick aluminum 6061, and I'll pick OK, and you can click on the material texture visibility in here, and it automatically applies a texture to your stock blank. Next, if you haven't already defined your tools, you can go ahead and create your tools, or you can even load your tools from your tool library. Visual Mill offers a wide range of tools, starting with ball and mills, flatten mills, corner radius, V-mills for engraving, chamfering. You have taper tools, thread milling, face mill cutters, dovetail, fillet mill or corner rounding tools. You got lollipop cutters, form tools or user-defined tools, and of course you have the drill, center drill, reamer, tap, bore, and reverse bore. Now you can have tools defined under each of these tool types. You can also assign your properties for the tool, and as you go over to the feeds and speeds tab, you can also have Visual Mill help you compute recommended feeds and speeds based on the parameters, the stock material, the tool material, the tool diameter, and other properties. So once you establish these, you can save these tools to a library and load these tools on all the parts that you like to program. Now we got the tools loaded from a library in here, so now I'm going to go ahead and program some of the two-axis methods. We'll start with two-axis and facing, so we'll select the facing operation, and then we'll pick the features for facing, so I can choose select drive containment regions or select curve edge regions in here, and I'm going to go pick the edges on this part and select that as my drive geometry. In the next step, I'm going to specify a tool for it, so I'll grab the face mill, set the feeds and speeds. By going to the feeds and speeds tab, I'm going to use the load from tool. In the next step, I'm going to establish my clearance to a saved Z height. It's set to automatic, so automatically it'll figure out the saved height for all your transfer motions and non-cutting motions. In the roughing tab, I can specify the parameters for the facing operation, specify the step distances in here. Under cut levels, you can specify the total cut depth. So the geometry, what I selected, I can say pick top and specify where to begin the cuts from. I can snap to the origin right there, and then I can specify my total depth by just snapping to 2 points. And there's my total depth of the 1/4 inch. I can do it in one or multiple passes, specify entry and exit parameters in here, and then I would go click generate to have it compute the toolpath. So there's your facing toolpath right there. You can switch over to the simulate tab. You select the operation in here, and you can hit the play button to run the verification. You can also toggle the display of the holder, and you can turn off the display of the texture and the toolpath visibility as you're running the simulations in here. There it is. Quite simple. Now the next step, I would like to program these pockets in here. So before I program the pockets, I'm going to go ahead and create some machining regions from this model. So I would go over to the regions tab, and I'm going to go into the region filter, and I'm going to choose ignore the inside innermost areas and define a flat area region by picking the space. So you'll now notice that VisualCAM automatically creates a region for the pocket. I'm going to repeat the same step by flipping the region selections in here, and I'm going to create a region to basically pick the flat area again in here, so I can create a region for this pocket in here, right there. Okay, so now I would like to program this pocket in here, so I'm going to go over to two-axis milling, select pocketing, and for the machining regions, rather than selecting the face edges, having to go through the process of picking each of those face edges, since I have a predefined region in here, I'm going to use select predefine, and I'm going to pick the first flat area region right there, which basically is for the first step on the pocket in here. I'll pick that as my machining region. I go to my tool, specify a tool, set the feeds and speeds, define the clearance. The workflow is very similar to how we program the facing operation. Now we'll specify the cutting parameters. You can specify your tolerances, your stock element, stock to leave. If you want to leave any side stock or wall stock, you could choose from one of these available cut patterns, specify a cut direction, set your step over control in here. You can also enable corner cleanups. You can add cleanup passes, go over to cut levels where you can specify the location of geometry, and you can also pick the cut depth directly from the part. And there it is. You can also specify your entry and exit parameters for the pocket operation, and then click generate, and there's your pocket toolpath that's been programmed right in here. So as you see, your pocketing toolpath has been programmed. You can click on display the toolpath to view the pocketing toolpath, and then go over to the simulate tab, hit the play button to run the simulation. You can also hit simulate to end to run through it. Now we'll repeat the same pocket operation for the pocket with the island in here. So I'm going to make a copy of this operation, right click copy and paste. And now I'm going to edit the operation in here and remove the current selection. I'll pick the inside edge, inner edge of the pocket as one of my regions. And since I also have an island in here, I'm going to use the select flat area regions to go pick this island top face. So we now have two regions selected for the pocket. We'll use the same tool, the same parameters of feeds and speeds and clearance, and we'll use the cutting conditions where we want to leave some side stock along the wall. So I'm going to leave 25,000 stock, and we'll specify the depth in here. So I'm going to pick the total cut depth, just pick 2 points, one on the top edge, one near the floor of the part. So the total depth is 1 3/4 of an inch, and now I would like to basically step it in 1/4 inch increments. And I'll pick generate. Now you'll notice that it automatically identified the topology of the part based on the drive curves that you selected, and since you have an island in here, selecting clear flats, clear island tops will automatically add an additional pass to clean up the top face of the island. So VisualMill will automatically honor the Z height of the drive geometries that you selected, and with the clear island top selected, it automatically also finishes the island tops. And there's your simulation for the deeper pocket. And you could always pause and then skip the simulation by selecting Simulate to Mill. There it is. Now finally, I'm going to go ahead and program a profile operation to finish this up. So we'll go to 2-axis and select Profiling, and we'll now pick Select Flat Areas. I'm just going to pick the floor of this part. I have the part selected. We'll grab it to 1/2 inch end mill. The same set of parameters for feeds and speeds and clearance. Under the cutting parameters, I'm going to choose Determine using 3D model, so the system will automatically determine which side to place the cutter. Specify my cutting conditions, entry and exit, and then select Generate to create a toolpath. And there it is. So this basically gives you an overview of the 2.5-axis methods that are offered in VisualMill's module from standard through Pro and Premium configurations. Now let's take a look at the high-speed pocketing toolpath that's offered in VisualMill. So I'm going to go ahead and open up one of these files. And before I do that, I just want to quickly show you, once you have these toolpaths programmed, you could take a look at the information which tells you how long it's going to take to program each of these parts. You can then post-process these out to your machine by right-clicking on the operation and then selecting Post. Specify your file name, destination folder, and then select Post. And there's your posted output file. You can also generate a shop documentation where you can basically create a setup information sheet. This will allow you to basically have the operator in the shop floor prepare the necessary tools, prepare the stock plan, the workpiece for machining the part, and the shop documentation can then be handed out to the machinist in the shop floor. So there is your shop documentation for the part you just programmed. Now let's go ahead and focus our attention to the high-speed machining toolpaths. Okay, here we go. So here I have a part which has several pockets on it, and I would like to showcase one of the very nice toolpath methods that's high-speed pocketing, which is offered in all of our configurations. So the workflow is very similar. Go ahead and select your machining features. In this particular case, I'm selecting the floor of these pockets. You specify a tool for it, specify feeds and speeds and clearance. Under high-speed cutting parameters, you can specify your tolerances, stock elements, and you can choose your cutting pattern, whether you want to do cut direction, climb, or conventional, and you specify your depths and then pick Generate. Now high-speed pocketing is a very nice toolpath method which basically uses a constant cutter engagement, starts it with a spiral toolpath and creates a toolpath with a constant cutter engagement, so it basically has tangential arcs. This would help you in prolonging tool life and reducing tool wear. So this is a great method for those of you who are looking for some high-speed milling methods. And this is offered in all the configurations of our mill module. Now the next thing I would like to focus on is one of the very nice features that's offered in VisualMill is hole feature detection. Before I turn the attention into 3-axis milling, I would like to go over the hole feature detection methods that are offered in our VisualCAM mill module. Now this part, the one I have loaded here, has several hole features on it, and I'm going to turn the attention over here to the Features tab in the Machining Objects browser. So I'm going to go ahead and have the system automatically identify all of the hole features on this part. So I'm going to use this feature called Create Hole Features. I'll pick this floor of the part, right click on it, and you'll notice that it automatically identifies 6 features on the part. So there's one whole feature and each of them has 6 instances. So all the features have been identified on the part. Now you can easily program these features by clicking on create whole feature machining operation, and you can notice that the system automatically displays the cross section of the hole that needs to be programmed. And from the available operation types in here, you can choose the type of operations to be programmed. So typically you would want to do a spot drill operation, so I could start out with a center drill, and then I would want to do a deep drill operation and maybe a hole profiling operation. So I'm going to drag and drop these operations under desired operations. I can also specify the depths for each of these. I can either enter them in or use the spinner controls in here to specify the depths for each of these operations. And once you have the operations defined, you click on create whole feature mop set, and you'll now notice that these operations are automatically, they appear under your machining job. Now if you'd like to change or swap out the tools in here, you can basically go ahead and drag and drop the tools. So for example, for the center drill, I would like to use a 1/4 inch drill bit. I'm going to use the same 1/4 inch drill bit for the deep drill, so I'm just dragging and dropping the operation on top of it. And I'm going to use a 1/4 inch flat mill for the hole profiling. Right click and then regenerate will compute the toolpaths. Now I'm going to go ahead and save these operations, the whole feature operations I programmed, over to a knowledge base, so I can reapply the same whole feature operations on a part that has exactly the same whole features on a similar part. So what I'm going to do here is now go ahead and load in another part which basically has an exact match for the whole feature. So you can notice that I have another part has identical whole features. So first I'm going to go ahead and identify the whole features from the part by selecting the face on the part. The whole features have been identified, and you'll now notice that there's a feature called select matching knowledge base and create whole features. So in this process, VisualCAM will automatically go look through your knowledge base of whole features, and if it finds an exact match, it'll automatically go ahead and generate your toolpath. This is a very nice productivity feature, so you don't have to go through the process of reprogramming the same operations on different parts when it finds an exact match for the same whole feature. So you can build your knowledge base library of, for different whole features, and the system will automatically go find those for you when you do a select matching knowledge base and create a whole feature.